Hello everybody. Today, we are going to discuss about spillway. Types of spillway, profile of Ogie spillway, energy dissipation below spillway, stilling basins and its types. This presentation is prepared by Anis K. Assistant Professor. Department of Civil Engineering. MEA, Engineering, College, Parenthal Mana. When the water in the reservoir increases, the large accumulation of water endangers the stability of the dam structure. To avoid this, a structure is provided in the body of a dam, or near the dam, or periphery of the reservoir. This structure is called as spillway. Mainly used to discharge water during flood period. Requirements of a good spillway are: provide structural stability to the dam under all condition. Should able to pass the designed flood without raising the reservoir level above high flood level. Should have an efficient operation. Should be economical. Spillway can be located within the body of dam, at one side or both sides of dam, separated from the body of dam. Different types of spillway are: straight drop spillway, ogee or overflow spillway, side channel spillway, chute or trough spillway, shaft spillway, siphon spillway, conduit or tunnel spillway, emergency spillway. The diagram shows straight drop spillway. It is the simplest type of spillway. It is in the form of a low height weir having downstream face either vertical or nearly vertical. Water drops freely from the crest and underside is modified to prevent fluctuating jet. Sometimes the crest is extended in the form of an overhanging lip, to direct the discharge away from the overfall section. Next one is ogee or overflow spillway. This is the most common type of spillway provided on gravity dams. The profile of the spillway is S-shaped. The overflowing water is smoothly guided over the crest and profile of the spillway so that the overflow water does not break contact with the spillway surface. If this is not assured, a vacuum may form at the point of separation and cavitation may occur. In addition to cavitation, vibration from alternate making and breaking of contact between the water and face of the dam may result in serious structural damage. Side channel spillway. When the dam is not rigid, and it is undesirable to pass flood water over the dam, this type of spillway is used. In this type of spillway, the flow after passing over the weir or ogee crest, is carried away by channel running essentially parallel to the crest. Discharge characteristics of this spillway is similar to that of an ordinary overflow spillway. The figure shows a side channel spillway. Diagrams shown here are chute or trough spillway. In this type of spillway, water is conveyed from the reservoir to the river below the dam, through an excavated open channel which is fairly steep in slope. Next type of spillway is shaft spillway or drop inlet spillway or morning glory spillway. It is the type of spillway which has horizontally positioned lip through which water enters and then drops through a vertical or sloping shaft, and then to a horizontal conduit, which convey the water out of the dam. This type of spillway is used when there is inadequate space for other types of spillways. Now we are coming to siphon spillways. It consists of a closed conduit system formed in the shape of an inverted U, positioned so that the inside of the bend of the upper passageway is at normal reservoir level. When the water level in the reservoir rises above its normal level, water flows over the crest. There are two types of siphon spillways: saddle siphon spillway, and volute siphon spillway. Conduit or tunnel spillway. In this type of spillway, a closed channel is used to carry the discharge from the dam. The closed channel may be horizontal, inclined or vertical through the dam, or a conduit constructed with open cut and backfilled with earth materials. Emergency spillway. This type of spillway is rarely used. It is an extra spillways provided on a project, in rare case of extreme floods or emergency. They are used to convey frequently occurring outflow rates. Next we have to study about the profile of Ogie spillway. The Ogie profile to be acceptable should provide maximum possible hydraulic efficiency, structural stability, economy and should avoid the formation of objectionable subatmospheric pressure at the surface. Fig A shows the flow over a sharp crested weir and Fig B shows an ideal spillway, which should have the form of the underside nap of a sharp crested weir. When the flow rate corresponds to the maximum design capacity of spillway, the head during an unanticipated flood may rise higher than the design head, which is shown in Fig C. In this situation the lower nap of the falling jet may leave the ogee profile, which leads to the development of negative pressure and cavitation. When the head on the spillway is less than the design head, the falling jet will adhere to the profile and develops positive hydrostatic pressure, which will result in the reduction of discharging capacity. Now we are heading to the next topic, that is energy dissipation under spillway. The water flowing over the spillway acquires a lot of kinetic energy by the time it reaches near the toe of the spillway, through the conversion of potential energy into kinetic energy. If arrangements are not made to dissipate this huge kinetic energy of water, and if the velocity of water is not reduced, large-scale scour can take place on the downstream side near the toe of the dam and away from it. These arrangements are known as energy dissipation arrangements or energy dissipators. The kinetic energy of this supercritical flow can be dissipated in two ways. By converting the supercritical flow into subcritical flow by hydraulic jump, or by directing the flow of water into air, and then making it fall away from the toe of the structure. The energy is dissipated by the aeration of jet and impact of water on the river bed. Though some scour will take place, but it is too small or too far away from the dam to endanger it. Bucket-type energy dissipators work on this principle. The energy dissipation depends on the Froude's number of incoming flow before the hydraulic jump. The variation of energy dissipation with respect to Froude's number of incoming flow is shown in the table. Based on the Froude's number of incoming flow, different types of protection works are provided for energy dissipation. When jump is weak and energy loss is low, no blocks or any other devices are provided. When jump is troublesome and oscillating, which gives rise to heavy waves on the surface, wave suppressors are required in this range for the length of jump given by the equation mentioned. When jump is steady, the length of jump is almost constant and hence, the energy dissipation arrangement should have the sufficient length accordingly. For large spillway long expensive stilling basins may be required, some auxiliary device may be used for further stabilizing the flow, and to reduce the length of basin. When jump is strong, it is likely to be rough also. Hence a bucket type of energy dissipator is preferred, to a stilling basin of hydraulic jump type. Next we are discussing about stilling basins. Stilling basins are external energy dissipators placed at the outlet of spillway. These basins are characterized by some combination of chute blocks, baffle blocks and end sills, designed to trigger a hydraulic jump in combination with a required tailwater condition. With the required tailwater, velocity leaving a properly designed stilling basin is equal to the velocity in the receiving channel. There are various types of stilling basin designs, such as USBR stilling basin, Indian Standard Basin, etc. Stilling basins are concrete aprons, provided with some auxiliary devices, such as chute blocks, baffle blocks, and end sills. These auxiliary devices can help in dissipation of energy of flow by offering resistance to flow and stabilizes the flow in a shorter length of basin. In general, stilling basins are structures in which energy dissipation is done, and if the phenomenon of hydraulic jump is used for dissipating the energy, then it is called hydraulic jump type stilling basin. Now we can see various components of a typical stilling basin in the given diagram. They are chute blocks, end sills, and baffle walls. Chute blocks are row of small projections, provided at the entrance of stilling basin. The incoming jet of water is furrowed and partly lifted from the floor, producing a shorter length of jump, than what would have been without them. They helps in stabilizing the flow. And sill are provided at the end of basin. They diffuses the residual portion of high velocity of jet reaching the end of basin. Thus helps in dissipating residual energy and to reduce the length of jump or the basin. Baffle wall or baffle piers are the blocks, placed within the basin. Across the basin floor. They help in breaking the flow, and dissipate the energy mostly by impact. They are also known as friction blocks. Baffle walls are more suitable for small structures. Due to cavitation under high velocity jets, this baffle walls becomes unsuitable for large structures. Now let us check what are the Indian standard types of stilling basins. Indian Standard Institution has standardized the stilling basins to use under different conditions. A full decryption of such basins are available in IS 4997-1968. There are 4 different types of Indian Standard stilling basins. Stilling basins having horizontal apron are Type 1 and Type 2. Stilling basins having sloping apron are Type 3 and Type 4. Figure shows Indian Standard Type 1 and Type 2 stilling basins. Indian Standard Type 1 stilling basins are used when fraud's number of incoming flow is less than 4.5. It is used under small dams or weirs. Indian Standard Type 2 stilling basins are used when fraud's number of incoming flow is greater than 4.5. It is used under medium or large-sized dams. Figure shows Indian Standard Type 3 and Type 4 stilling basins. Indian Standard Type 3 stilling basin is provided when the depth of jump is less than tail water depth. It is provided under submerged jump for all discharges. Indian Standard Type 4 stilling basin is provided when jump changes as submerged under different conditions. For this type stilling basin, a portion of floor is sloping and other is horizontal. Here we are going to discuss about different bucket type of energy dissipators. In this diagram, we can see roller bucket type energy dissipator. Here we can see slotted roller bucket type energy dissipator. Here we can see ski jump bucket type energy dissipator. Thanks for watching.